First of all, thank you to Ugo and all organizers of this wonderful conference. I said all organizers. So I am a PhD student in the muscle biology lab of Maynooth University, working under Professor Kai Olendiek. Our research is mainly proteomics-based analysis of dystrophic muscles and organs with the goal of identifying novel biomarkers of dystrophinopathy. So I know there's a lot of experts of DMD here, but not everyone, so I'll give a brief introduction. So Duchenne muscular dystrophy, or DMD, is caused by the almost complete loss of the membrane cytoskeletal protein dystrophin, and in particular the isoform DP427. So we can see the difference between normal muscle and dystrophic muscle. It's almost non-existent. So dystrophin, or DP427, is a key component of the dystrophin glycoprotein complex. And in this image we can see the dystrophin core complex containing DP427, dystroglycans, sarcoglycans, sarcospan, syntrophin, and dystrobrevins. And normally the dystrophin glycoprotein complex is involved in roles like the mediation of lateral force transmission from sarcomere contraction to the endomysium, and the revision of sarcolemmal membrane integrity. Okay, so some more immunofluorescence images. Again, we have DP427 showing the reduction in mdx. So mdx, for those unaware, is the mouse model of Duchenne muscular dystrophy. Also showing the reduction of carbonic anhydrase 3. So CA3 is an enzyme that mediates the reversible hydration of carbon dioxide. And in X-linked muscular dystrophy, we see a reduction of CA3 in skeletal muscle, and we also see an increase in serum. So last year, we published a review paper focused on proteomic profiling of CA3 in skeletal muscle. And currently, in our lab, we're working on an experiment comparing the proteomes of mice diaphragm muscle from 4 different groups of mice. So the groups of mice are young wild type, young dystrophic, aged wild type, and aged dystrophic. The young diaphragm is from 3-month-old mice, while the aged is from 15-month. So we took 6 diaphragms from each subgroup, and we performed comparative bottom-up proteomic analysis, the process of which is seen on the screen now. So the bioinformatics program Panther was used to summarize the clustering of protein classes in the mice diaphragm. So we can see that the 2 largest classes are hydrolase and oxidoreductorase, while other large classes being transferase and cytoskeletal. Okay. So on to some proteomic changes that we observed in our study. So first of all, we can see that collagen 6 is much higher in the aged MDX, or the aged dystrophic group, than the other groups. And as I mentioned earlier, the dystrophin glycoprotein complex is involved in providing a structural link between the extracellular matrix and the actin cytoskeleton. So by doing this, it provides stability to sarcolemma, and when the dystrophin is no longer present, we see that the muscle fibers become a lot more fragile, which can lead to fibrosis and can result in the accumulation of extracellular matrix proteins such as collagen. So we can also see that the proteins junctophyllin 1 and CA3 are higher in the young wild type compared to all the other groups, whereas proteins such as heat shock protein 27, annexin 5, and 14-33 beta alpha are highest in young dystrophic. So this study is not published yet, but we have some preliminary immunoblots completed. So we can see confirmation of the collagen 6 being highest in the age dystrophic, and we can also see that junctophyllin 1 is highest in the young wild type. And just to further show the accumulation of collagen 6 in the dystrophic muscle, along with the reduction of dystrophin DP427. So finally, we just have a table summarizing the protein changes that we see during the aging process. So the major changes that or the major trends in change that we see is slow to fast transitions and glycolytic to oxidative shift. So before we publish this paper, I'm hoping to get a lot more immunoblots done on a good few of these proteins, especially the myosins and GAPDH and a few others. So that's all. Finally, just some acknowledgements to my supervisors, Professor Kyle Endiek and Dr. Paul Dowling, and to our associates in the University of Bonn who provided the diaphragm muscles for the study, Professor Dieter Svandula and Margaret Zweier. And lastly, to the Kathleen Lonsdale Institute for Human Health Research for providing funding for this study. And thank you all for your time.